Okay, welcome everyone to this webinar, FEFLOW webinar. In the monthly webinar today, we will be talking about 3D and structural meshes. So it's always quite good to see a lot of interest in this topic. So basically today in the webinar, I will make a review of the existing workflows that we have. So in case you never work with this type of meshes in FEFLOW, will be quite interesting for you. At the very end of the presentation, I will show something about the new workflows. And since the next week, we have, again, a FEFLOW release, so we will be releasing 8.1. I will shortly show you a few small things about the release, and more of this will become in the next webinar on the 30th of November, which is fully dedicated to the release. My name is Carlos Rivera. I'm the Global Product Specialist for FEFLOW at DHI. I am located in Berlin, in Germany. I would like to welcome you to this webinar. So the agenda for today, we have some short announcements. To start, a quick introduction about FEFLOW. We'll be talking about different workflows for meshes, new workflows for 3D Supermeshes. I will do a short live demonstration. Okay, so as I was mentioning, we are really celebrating next week the MIC 2024 release. This comes with FEFLOW 8.1. We have 6 big features related to different topics on different applications from mining, groundwater resources, and geothermal. So we have integrations, new integrations to CAD systems. We have changed a lot the way of how the well manager works, integrating groups and rules. For those ones working in the geothermal sector, we have a lot of new features on that aspect. We have consolidate a way how FEFLOW compares simulated results and observation data. So we have a new dialog called observation data dialog, which help you to control information of the process variables, so observation points, budget groups, but also content domains. We have a new interface of Python. It's quite nice. It's the first time that with one single Python script, you will be able to build the entire model domain from scratch. So we have opened a door to access Supermesh documents, mesh generators, and also exchange or extend the model to 3D directly from Python. And today I will be talking part of these 3D Supermesh tools. Most of the discussion, as I say, about these release features will come in the next webinar on the 30th of November at 3 p.m. UTC times, which is 4 p.m. Central European time. Okay, so for those new, so FEFLOW is a finite element software already being around since many years, since the late 70s. We have been developing FEFLOW since that time. FEFLOW is capable to simulate flow, contaminant transport, groundwater edge, and heat transfer under fully and variable saturated conditions. We have 3 cores, so when we develop the software, we go in the direction, or our vision is to have a software with the concept of all-in-one solution. So we develop the graphical interface, but at the same time, we develop the different methods in the engine, calculations. In the last years, there was not many changes on the calculations. This is going to happen in the release of 8.2. And depending on the type of development period that we have, sometimes we focus more on the usability, and other times we focus more on the numerical methods. So the next release, 8.1, is a lot on usability, a lot of on workflows, how to do the things faster in the software. The next release in November 2024 will be focusing more on numerical methods. We also have as a principle that we want to have a software that give you a workflow where you can save time, you can boost efficiency, you can do many things with the software from the graphical interface, but also from the programming interface. And we give also a lot of importance into the visualization in FEFLOW. So FEFLOW is one of the most extensive groundwater softwares in terms of visualizations, where you can easily create cross sections, 2D views, 3D views, animations. You can clip the model, carve into the model, use virtual reality to present some results, etc. And as we say, we want to have a software that is all in one and support you from the very beginning, that is the conceptual model, until the final part of the workflow, where is calibration and model prediction. Today, we will be talking about the first part, conceptualization and meshing. Today, we will be talking about 3D meshing. 3D meshing, in simple words, means that we have extended the library of finite element methods, and this is something not done recently. Since the version 7.0, we have the possibilities to introduce 3D and structural elements. And structural elements in 3D will be tetrahedral, prismas, hexahedrals, and others. So we basically extend the library, where give us the flexibility to introduce new type of elements and therefore accommodate to complex geometries. I have been using this slide since many years, so I see some of the names in the list of participants. You know these slides. So this time I need to really change a bit the way how I typically explain. So normally we recommend to use unstructured meshes where it's really necessarily when you need to pinch out layers, so you maybe need to introduce some casted networks, or you have some faults or inclined boreholes and others. Typically, it's recommended to use layer-based models because it's easy to work, so you can go to the slice view, and in slice view assign some parameters and then compare or double check this information in the 3D view. And if you have a clean structural model coming from the geological software or from any 3D software that allow you to build the structure of the model, then you can import this model into FEFLOW, and then we build a 3D full and structure mesh. So there are three main workflows, and these workflows are available since already many years. So what we have been doing in the last year was to improve some of these workflows to make it more user-friendly, or in sometimes, depending on the data available or the imperfections of the data, the workflow was not completely finished until the end. So now introducing new methods in FEFLOW, we secure the possibility to build 3D and structure meshes. So the most simple option that you have is via the layer configurator. So this is a workflow that everybody who works with FEFLOW should know, where you have point data, and using this point data, FEFLOW could interpolate using kriging, invert distance, or Akima methods, and then create set of different surfaces or slices, what we call in FEFLOW, to construct the structure of the model. The nice thing of the layer configurator is that you have the possibility to create rules according to the classes. We have two classes, fixable and movable, and with these two classes, you are able to build many complex models. The classes indicate if it's fixed, and if you are interpolated, and this interpolated surface is contact or is touching any fixed surface, then FEFLOW knows where to stop this layer. And you can use this method to construct complex geometries. You can, for example, have a case where it's outcropping here, and then the topography is fixed. So FEFLOW will know that the slices conforming the layer in yellow have to stop in this location. And this brings to a situation where there is a slice intersection, and in this case, FEFLOW offers you a number of possibilities how to solve this slice intersection. Few examples about this. So if you would like to put a fault in the middle of your model domains, or a fracture, or any structure, or a surface, let's generalize this, a surface that is in the middle. So that's the way how to build a model. So you will add first the 3 layers, so 4 slices, and then you will add the one in red in the middle, and then you interpolate, accommodate to the right slope of the surface. And then before previously you have marked these slices 1 and 2, 4 and 5 as fixed, then FEFLOW knows where to stop, and it will create a zero thickness for this in between the red and the yellow lines. Or you can have parallel or quasi-parallel faults. So after you are done with this step, you can go to the next one, include a slice, and then change the elevation, and FEFLOW will stop here. In the first exercise of the demonstration, I will explain you these configurations. Or you have two faults in between red and green, and you would like to add a tiny layer. So the 5 has the right location, 6, 2, they are marked as fixed, and FEFLOW, after you interpolate the new slice 4, it will stop exactly at this point because of the condition of the horizontal class. Or the other possibilities where you can continue slices on the left or on the right of the fault. Okay, so you have a 3D model. The model is parameterized, and sometimes comes the typical question, okay, we want to make a change in the model, but we have already parameterized, we have already calibrated, we are very confident with our modeling results and parameters, so we don't want to do many changes into this model. One possibility is to take this workflow number 2, where basically you will extract a part of the mesh, and this part of the mesh will be sent to our 3D mesh generator called TechGen, and TechGen will create a new mesh with a number of constraints that you are passing. These constraints could be new set of points, polylines. This could be a tunnel in the new volume, or a drainage system, or a polygon. And when the mesh is done, it will join this new mesh from the subdomain to the old big mesh from the regional model. And this is very practical, and is not much done. So that's what I like to emphasize in the webinar, although the technology is not new. Is very practical to introduce new geometries that were not previously in the model. So if you have a well-defined system of lines, so this could be a car system, or it could be a set of dewatering pipes, or anything. So you can take this part of the volume, and FEFLOW will remesh the volume and then connect the new to the old one as it was before. The workflow where we have been working the last years is this one, the number 3. And this number 3 workflow was introduced initially with the version of FEFLOW 7.0. And this is a workflow where we see a lot of potential, and we have been investing in terms of meshes, in terms of usability, what new tools do we need in FEFLOW to make the life of the FEFLOW modeler easier. Basically, this workflow means you have a set of different maps. These maps are in 3D. The maps could be one single map containing all the information. In this case, will be a geological model, or could be a set of different surfaces, points, polylines, and all together define a conceptual model. When we import the maps, FEFLOW builds a so-called 3D Supermesh, and this 3D Supermesh is then used to constrain the mesh generator. So that is an example of a 3D Supermesh. It consists on 3 different things, so surfaces, polylines, and points. All the surfaces has to fit together, all the polylines exactly. The major advantage of this workflow is because you already start from the very beginning with a 3D geometry. You have the possibilities to store all the data that you require during the meshing process. So if you have geological blocks being defined through the structural model, these blocks will be stored as elemental selections in FEFLOW. So if you want to parameterize, then you can just simply activate the elemental selections. In case you have lines represented pipes or drainage systems, this will become 8 selections. If you have faults, surfaces that are defined at different structures of the model, these will become phase selections. So the major advantage of the workflow is to have a 3D representation of the system, but also to store all the data already coming from the 3D model into the FEFLOW selections panel. So we support a number of file formats. These file formats, so typically the user will go from a geological model. So we have these options, so 3D GeoModeler, GoCut, Leak4Meshes, and MikeSign, which works with the standard DXF files. But it's also recommended to use other extensions, or combine these geological models with other file formats like shed files, or sometimes You don't need to put your details or technical details inside the geological model, so you can store this information outside and combine with shed files, AutoCAD files, Autodesk, and also the file formats from the mesh generators. As I said before, motivation is to try to put most of the information into the FEFLOW model and do not simplify the geological model or the conceptual model in order to fit a limitation of the software. No? So we try to get as much as possible of the data. So this is a all example done with GeoModeler 3D, where you can see the different structure, the tetrahedrals being clipped by the planes in FEFLOW and the fully 3D model. So the major problem with this is the definition of what we require to create a tetrahedral mesh or volumetrical mesh. So we use a mesh generator called TechGen, and TechGen follows this PLC, piecewise linear complex. In simple words, means you have a number of structures, geometries, and these geometries, they need to fit perfectly. So if you have surfaces, you should imagine that everything is a big puzzle, and all the surfaces need to fit in terms of the segments and in terms of the different vertices. Cases like the ones here on the middle and on the right side, where you have a surface, this is maybe a geological contact being intersected by a segment, by a pipe, or by a tunnel. This is considered as a mistake in terms of input for the mesh generator, and it will throw an error message called self-intersection. So basically, the geological model or the software that is used to create this input data needs to contain a point which represent the intersection between the plane and the line, and this point needs to be connected to the three vertices. The same here, if you have horizontal geological horizon and then intersection between other horizon or a fault, then you have this intersection. This line has to be represented in the input data. This case is very common and happens a lot in cases where the geological models or the geological values are being exported as one single file or in different pieces. And then there is a fault model, which is also exported, but maybe with a different triangulation or resolution. So they are not fitting one-to-one, and the mesh generator will detect this problem and then will not allow you to continue. So that was the situation until we introduced FEFLOW A0. And I'm going to explain you what we have done and what is actually coming next. So that's a very simple example of this PLC that you know, so how it looks like. So that's another example of a geological model here, which is very simple, 3 layers. This is the input taken by FEFLOW. It's not a mesh, it's the input used to create the 3D super mesh. You immediately can see there is a lot of details that might want to improve or change. We have a coarse discretization on the top, a finer discretization in the vertical surfaces, some triangles being connected. So all this input data, if you take it as it is, will affect your your resulting final element mesh. So that's the example. If we clip the geological model and at the same time we clip the FEFLOW model, so FEFLOW preserves very well the geological contacts, but is probably in this case emphasizing a lot the discretization around the vertical faces because the input data comes in that manner. So we need to improve this, and it's not that easy to improve it directly from the geological software. That is why we take the next steps in our developments roadmap. So this is the example of the self-intersection where you see surfaces well discretized, not coinciding with the other core surface. So this is gonna throw an error. We can look at here in detail. So the faults are very refined and the surface on top is very coarse. Okay, so if you have a mesh, if you have a proper 3D super mesh, we have also the possibilities to implement the definition of materials directly in the super mesh using the concept of the parameter lookup table. With the idea that you put everything before the mesh is created. When you create a mesh, during the meshing process, FEFLOW will parameterize automatically the entire 3D model domain. Okay, we know now the limitations that are happenings in these cases of 3D super meshes. So how do we resolve these problems? For this, the last year we implement a new module called FEFLOW Advanced. This module is a so-called SMA benefit module, um, which means that it's given to users with active maintenance agreement. So basically, the module brings a new technology called GOD. So we work with a company in France called GOD Solutions. They are expert in 3D meshes. We have been working with them already for some time. We introduced these modules into FEFLOW, and they provide us the capabilities to repair improper 3D data sets. 3D data sets will be surfaces of polylines. So if we are able to repair these data sets, we will be able to provide a proper 3D super mesh and therefore finally create a final element mesh in FEFLOW. The other advantage is that we want to also have a living model. So you are done the 3D super mesh, sometimes comes new changes in the geology. So we want to integrate easily the possibility to change the 3D super mesh in new surface coming into the workflow of the project, so you can update to your 3D super mesh easily with this workflow. So far, there are only two methods implemented. So we are in the next months or next year, basically adding more methods. We did it like this because we want to get feedback from the users and try to understand what is the best workflow that we should accommodate or improve. So the first workflow is called remesh. It's a very simple idea where you pass any surface and the workflow on the tool allows you to retriangulate, to create a surface retriangulation. The benefits are significant. So if you pass this surface, which could be a topographical surface, could be a raster, or could be anything in any format supported by FEFLOW, you can call the tool and say, okay, refine this or not refine, retriangulate this with a given triangle size of, in this case, 250 meters, and it will provide Delaunay triangulation. You can also go more and refine and increase the level of details. You can do the opposite. Sometimes you get a surface which is very well refined. So we have a resolution maybe of 10 meters by 10 meters in the topography, and we don't need this. So we can decrease the size and we can create a core surface from this input. Remesh can be also seen as it has some possibilities to preserve specific features, what we call sharp features. A sharp feature is a segment in this example, and this segment preserve the shape of in this case, the cube. We can tolerate to not preserve these sharp features, and basically the cube can be slightly deformed. Why do we want this? Is because if we are again looking the concept of topographical surfaces, where maybe we already know that this comes from interpolation, so we might want to tolerate certain flexibility to accommodate and get a better triangulation in the surface instead of just fixing something which could add additional or unnecessarily constraints to the later mesh generation process. The other workflow is called repair, Supermesh repair. And as the name says, it repairs the improper 3D data sets. To make it very simple, I have the example of a box. So the example that I will show later in the demonstration with a plane. The plane is extended outside the domain. So if you pass this to the mesh generator TechGen, it's not going to work. So using the Supermesh repair, you can basically just throw out parts of the surfaces that are not necessarily, and FEFLOW or GOD solutions will take care of the connection in between the intersection of the plane and the topography and the outer faces of the box. And with this, I would like to really jump into the live demonstration and then have enough time for questions. So you see, I'm using FEFLOW A1. So this will be already published next week on the 22nd. I think it is a Thursday. No, it's a Wednesday. So you will get this version of the software from our website. So from the first impression, there are not many changes in the graphical interface, but there are. So I just keep some of these. I will show you a few things, but most of these we will be explaining in the next webinar. So I start with a very classical example where it's called, where we have a 2D mesh. And this is example that I use in my trainings for mining applications where we have open pits. So the different lines corresponds to the mining plans. These are surfaces or topographical information already stored in the FEFLOW model as user data distributions. So that's also a workflow that exists in many years and is not much used. So you can store any type of information here and later use this information to create a mesh. So the model is only in 2D, and we are going to run a workflow to the workflow number 1, which was in my presentation, to construct a 3D structure mesh. So since we don't have too much time, I have prepared a macro. A macro allow me to record all the different steps that I'm doing in the layer configurator, and I can go back before the 3D mesh is created and run the macro as many times as I want with different even 2D meshes or even domains, and I will be able to reveal the model quasi automatically. So let me play the macro, and then you can see immediately how the mesh is built using the user distributions from the file, but also a set of different external point data sets. So we have we add some folds here, and we also have some vertical layers with some continuous thickness. So if we press OK, so this will be the first experience with the 3D structure meshes in FEFLOW. So maybe it happens to you and in situations where you didn't expect. So because the elevation was touching different surfaces, and now FEFLOW is going to ask. So here we are going to say that we want to take the entire model domain and create a full structure mesh. Also, details to know here is when we do these meshes, from the layer configurator, the option of quality mesh is deactivated because it is expected that the user goes in the second steps and runs a workflow to improve the mesh quality. So now I'm going to create a mesh. So this is already one step forward, but I'm going to show you some. So the results of the 3D mesh process in FEFLOW basically creates a block of elemental selections following the shape of the different slices of surface. So we deactivate this, and since I have some topographical surface defined in different, in this case, it was the example of the mine, which I have it here. And so these topographical surfaces, they define in between some volumes, and these volumes are stored as elemental selections in FEFLOW. So we'll just repeat it in parallel. I need some files here. So we have some point data, and then if we add it, we can reveal this. I just want to show you the part of the mesh where there is not a quality mesh. So we can say it's now, and then we remesh the entire model domain. So, okay, so something is happening in my data set. Anyway, so what is creating this is a group of different blocks, and these blocks can be in the next step taken for parametrization. So we can activate the selections and then define conductivity values and anything that we want. Okay, so what I was saying before is that the mesh that is created is not a quality mesh. So what you could do, if that's the case, is the second workflow that I was mentioning in the presentation is basically take the volumes of the mesh, pass it to the panel, meshing panel under TechGen, and ask to generate a new mesh with a different set of with different constraints. In terms of constraints, what you could use in these cases are constraints to prescribe the maximum number of elements. So this is practical if you would like to refine the model. If you would like to even refine it, very fine the model, I prefer to use the global tetrahedron volume constraint. So you need to prescribe a volume of the element. We are not used to volume, so normally we use lengths. But if you would like to have an idea about these volumes, you can basically display this elemental volumes parameter and the auxiliary data section, and then you can see what are the volumes that we have. So you can also provide this statistical distribution of the volumes. What is the mean, the max values, and then take a value that is close to the upper boundary, and this value you can prescribe here. You can also constrain or create meshes refined by this facet area, hull facet area constraint. The hull facet area are the vertical faces of the domain. 100% is not, there is no constraint, so it's going to take the triangulation that you have, so each of these triangles that you have in the surface, and use it as the input for the mesh. If you say 10%, it's going to take each of these triangles and subdivide the area up to reach a 10% of the original area, and use this as an input. Analog is for the facets, so the facets could be any face selection, so if you have faults or any a structure that you would like to implement into the model. So here we have, in this case, we have this plane. So you can use this information. So you can drag and drop the planes here, and then use an in facet of 10% or 20% to include discretization exactly at the context of the faults. Segments analog, so you pass lines, polylines, or you can also add maps here, which are polylines, and then tell FEFLOW to use some constraints along the lines. The same for the points. Points could be nodal selections, but it could be also selections or no maps containing point data. And you can tell what is the volume exactly at the new node to be created. Then we have a number of options, preserve external boundaries. So normally you don't use because you want to create more elements after the layer configurator, so you don't want to be constrained by the external boundary. Preserve mesh entities is always true because you want to preserve the inner structures that are coming from the layer configurator, or if you have already a layer-based model, you don't want to lose the layering that you have in your system. And that's the way how you improve your mesh quality on your discretization. So this will be the workflow number 2. So now let's move to the other option, which is let me open another file. So I have already import a surface to save some time. And this is the surface that we are going to use for the exercise. So in the new interface of FEFLOW, it looks like this. So you have a bunch of new tools to create geometries, to select, to export, to delete, to snap, because we noticed that there is a lot of possibilities to do with geological softwares, but not anyone is able to work with this technology. So we want to offer certain flexibility to our users, where in some cases there are the input or the geometries that you want to create in FEFLOW are simple, so you can just build it directly in FEFLOW. And so how to start? We have the surface. This surface represents a topographical surface, so I can tell FEFLOW to build a domain from that by extruding the surface with a new tool. It's called Supermesh 3D bonding surface. So I have already a 3D mesh, and with this 3D mesh, I can just build a final element mesh with TechGen. But that will be too simple, so we can do a number of things. So we can for example, create a river on top, so we can add a polyline. This is something that which was quite complicated in the past. So if you have a river, so how do you put the river on the top if you have a structure model? So we have now the possibility to reproject a polyline on the top of the surface that you select. So basically you can choose the surface and it creates a line. And just to give you a very simple demonstration, so we can create a mesh out of that. But let's put another detail, so we can create a fold. We can draw the fold here and then indicate inclination angle. This is something which already exists in the current version, but now we have the possibility to add buffers, so we can create a number of parallel surfaces which can be used to constrain the finite elements in between the surfaces, in case you want to simulate this fractal system as a finite elements, as a volumetric surfaces and not discrete features. And then if we call the repair tool, this requires a couple of seconds normally for this, and this gives you the outcome where you have the surface being thrown out the path that is not needed, and then if you call a remesh, then you can improve the quality. That's a issue with the polyline. Improve the quality. So the other possibility that you have is for cases where you have a simple geometry. So where let's repeat this exercise. So we can add now a set of points. So the points. Yep. Okay, so I have a set of points. I'm gonna visualize these points in FEFLOW. So we have some classification by a name, which we call horizon. Just give some colors. And now we can plot the data in 3D and make the line a bit thicker that is visible. So I have a set of points which corresponds with some contacts. I just, for time being, just put 4 points, but could be anything. And then we can use the tool to snap, and then we can start digitalizing our geological model. So we can snap to any external data or part of the domain. So I just make the surface a bit bigger so that it's visible for you. And then we can keep rotate the model. Sorry, my mouse is and then we can, with enter, we can close, and then we have a new surface. So obviously, if you have a number of points, you can do it perfectly. If you have many, so it's probably better to create a surface outside of FEFLOW. And I can show you also that if you want, or if there is a bit of time. So we can start digitalizing this. The next one. Then again, close, and then continue with the next surface. So with this, we can, for example, say, okay, let's imagine these are parts of our different horizons. So I just exaggerate the surfaces and make it quite thick that is visible. And then we can generate out of that some layers. So now we have the layers here. Then we can retriangulate so that we get rid of this not tetrahedral triangle. So now it's finer. I didn't change any setting here, target length 0, but you can, if you print the output in the log panel, you can see what it's doing. So it takes a length of 300 meters because it calculates the average size of the surfaces that we have. and then so that's why you see a quite regular size of the triangles in the surfaces. You can decrease if you see that use 300, maybe the next time you just say 150, and then you will have finer meshes. So now if we call the mesh generator TechGen, so we can go to TechGen, and now we have a 3D model in FEFLOW with the different blocks which were created because we were cutting the model in such a way that it's create closed surfaces, closed volumes. The information of these planes or polygons are available as well as a part of selections. So we have here every surface is also available here. Okay, so in case you forgot or you want to do something, you can go back. In the new FEFLOW, you have the possibility to select information. And if you don't need anything, you can just simply delete this. If you are happy with the distributions of the surfaces and how are they, and if you don't want to repeat again and again, you can simply export this data. This is the possibility to export any surface, export elements, and then you just import in another project. Now here we can repeat the case of the plane. So we can create a plane that goes like this, and then give some inclination, then put also some distance buffers, and then you can keep working with this project. So what I was mentioning at the beginning, we want to give possibilities to that you keep updating the model and modifying the Supermesh as many times is required. So now it's gonna draw the surface, so we can also see here in the information number of blocks. So I don't know how I draw the plane, but maybe I cut it. No, I think I cut it entirely. So you see the number of blocks that are generated. These blocks are also represented in the Supermesh, in the meshing panel as points. So if we activate, click on the points, and we will see what is exactly the block located. And these blocks could have material information. So if you have in parameters linked in a lookup table under the problem settings dialog, then you will be able to define your materials or different geological units, hydraulic properties, and link this information directly at this stage. So when FEFLOW generate a mesh, so you will be able to pass the hydraulic parameters to the final model domain. So if we run now the repair, so we can see here the number of vertices that we start, so 4,838, and now we are ending up with less vertices. The number of blocks is the same, and with this you can also create. Sorry, it was unintended. Create a mesh. The mesh is done, so we can open the FEM, and now we have different blocks because we have been cutting the domain by the different planes, and the rest of the information in surface is also updated. And with this, I would like to finish the live demonstration. And again, I would like to remember you that on the 30th of November at 3 p.m. UTC time, 4 p.m. Berlin time, we have our next webinar related to the release of 8.1. Today I show a few tricks about the 3D Supermesh tools and 3D meshing. In the release webinar, I'm going to show more in detail about this, but also all the different features that we have in the version. Thank you for participating in this webinar. It's a pleasure, as always, and I hope to see you in the near future. Take care, and until the next time. Bye.